This conference will now be recorded.
Okay. So, what question am I going to ask you? So, what does the SVM do? What's the main, like, how does it separate the hyperplane? What kind of hyperplane does it find?
Linear.
Yeah, linear, like logistic regression or the perceptron that we haven't, that we didn't do yet. But what kind of linear classifier? There are many lines, like in here, we have multiple. What kind of separation does it aim for?
The one like the best one, like that gives the distance between.
Yes, it's a margin maximizer. That's what we do. It's a margin maximizer. It tries to maximize the margin between the classes. Like this one. This is very close to what an SVM does. It's a margin maximizer. Not this one, not this one, not this one, this one.
Yeah.
Okay.
Are there any new slides for today's session?
Yes, yes. You want me to send it to you?
Yeah, if you could, that'd be good.
Okay, give me a sec.
Thank you.
I'll continue asking the questions. What is the purpose of C in an SVM? What does it do? The C parameter.
It's calculate the error.
But what does it mean? A low C or a high C? What is it going to mean?
For example, if it will be infinity C, that means it will be a hard SVM. Doesn't allow a hard margin. It doesn't allow many errors.
It doesn't allow any error. It wants to find the hyperplane that separates things perfectly.
Exactly. And the low C, it allows like a big margin, which
yeah, it
allows
tolerates
many
errors.
Yeah.
It tolerates misclassification, and even
yes.
it tolerates some points inside the margin.
Correct. Yes.
A hard margin doesn't tolerate anything inside the margin. Okay, so that's the purpose of C. So if C equals infinity, yeah.
So for the hard margin, are we saying, just to clarify, that C is infinity?
Exactly.
Sorry, zero.
Yeah. That was going to be my question. Yeah. If C equals infinity, we get a hard margin.
Oh, I thought it'd be the other way around.
Yeah. If C equals infinity, it means that the error is at its maximum. Any error is not accepted. So any error is not allowed. Like this is the error that you are seeing here. So if C equals infinity, any errors will make this infinity. The whole equation will become infinity. And we can't optimize infinity. We will never be able to optimize it. Like they will be all the same. Like when we have a single error or two errors, it will still be infinity. So if C is 0, then we are not, we don't care about making errors. Is it fine?
No.
Just look at the formula. If C equals infinity, the hard margin as VM doesn't tolerate errors. We agree on that.
Well, from what we spoke, when we discussed last week, I think hard margin SVM, you said, doesn't tolerate any errors, and it wants to classify everything accurately according to the training data set, right?
Exactly.
So if it doesn't tolerate any errors, I would have thought that C would be equal to 0 to make the whole equation 0.
No, it's the opposite. If C equals infinity, this is the error. Yes or no?
Yes.
This symbol.
Yes.
So if this is an error and C equals infinity, C multiplied by this equals what?
Infinity.
infinity, and we can't optimize anything here. This will not affect anything.
That means that's not good, right?
It's not good. It's not good for us. Yeah, we can't do anything to in this.
But wouldn't this be the worst case possible?
Yeah, a single error will make it the worst case possible. Single error here, because here we are summing the errors. We are summing the misclassification. So a single one will make it infinity.
This is what you mean by can't tolerate, is the fact that even if it has one single error, the whole problem fails, the whole solution fails.
Yeah, exactly. It doesn't tolerate any error. We can't optimize it. We can still optimize it, but we have to remove all the errors first, and then we can optimize in this one to find the best margin. So we need something that doesn't produce any error. Yes.
Yes. If how much we will tolerate errors depends on C.
Exactly.
Yeah. So what's the like the best value of C? Like what's the optimal?
It depends on the problem. You will never get a single answer to this question. It depends on your problem, and you have to try multiple C's.
Okay.
What is that thing called? Is C sum of errors I to n? Is that called regularization? What's that whole term called? I just want to write for my notes.
It's not actually a regularization. I don't really remember if it has a name, a particular name. So yeah, this can be called the loss function. Yeah, this one is the regularization that maximizes the margin. So we can call it the loss here.
Okay, the loss
How
function.
much loss we will have, yeah. But actually, in reality, everything is called the loss function, the cost function, actually. Okay.
Would you say that the C parameter, it controls the hyperplane, which in turn controls the accuracy of your result?
Yeah, it influences what we call the regularization parameter, C. It's also called the regularization parameter. And it controls indirectly the hyperplane by controlling how much error do we tolerate.
Okay.
Because the more we tolerate error, the more we can afford a bigger margin. So if you want a very big margin tolerating more errors, you can play with it on C and see if it helps or not.
So can C take the value of 0?
Of course, yeah, we can make it 0, but it won't be
and
very
useful. It means that we are tolerating all the tolerating all the
errors. Exactly, yeah. So we are just looking at the best margin, tolerating all the errors. It won't be. I can't even imagine what kind of hyperplane we will have. It will just be something not very useful. So never put a 0 in C. That won't be really good.
So in the soft margin, are we saying C can be anything apart from infinity?
Exactly, yeah.
Okay.
But it's more like a lot of gray shades. It's not like something that is very hard. It's more gray shades. How much error do we tolerate? And you can slide it and see how your model is performing, and so you can determine the best C. And this is just like a trial and error step. Like that, like there is no theory that tells you what is the best C. Nobody can tell you that. You need to rely on testing, and you have to try it multiple times and see what's the best C. We can talk about grid search and other ways of determining this C. Not today, but we can have a session about this. Bayesian optimization. This gives some very good results. It can even this is a technique called Bayesian optimization that deals with finding, because C is a continuous value. It's not a discrete value. It's not 0, 1, 2. It's like a continuous value from 0 to infinity. It's a positive continuous value. So there is what we call Bayesian optimization. It relies on some Gaussian mixture, and it can find in many cases better than data scientists. And I mean by the best data scientists in the world. It can determine the C better than them, this technique. We can have a slide about it next time. So this is about the C. So we have here everything about it, more or less. Another question. Okay, does the SVM, the regular one, the regular SVM, does it allow to classify non-linearly separable data, like in here?
Yeah.
How?
Introduce a lot of these, like a circle, for example.
Sorry, what?
We add another dimension.
Yeah, that's the kernel. You see the kernel trick. But without using it, can we still classify this?
Hard.
Well, yeah, the hard margin SVM will not find anything because there is no hyperplane that can divide this. No hyperplane can do it.
Yeah.
A soft margin SVM can find something, some solution, but it will probably be a bad solution. With the soft margin SVM, if it can tolerate some errors, say we tolerate like I don't know, 6 errors or 4, 6 errors or 7. If we tolerate 6 errors, we can find the hyperplane in here. But we tolerate a lot of errors in here. So this is a soft margin SVM. We'll probably maybe do this hyperplane. But it still be not a very good solution. So the regular SVM without the kernel will really struggle with this problem. Do you agree with me?
Yeah.
Yes. Yes.
Okay. So what do we do when we have this kind of problems?
We
What do we
add
use?
kernel.
The kernel, exactly.
Kernel.
We use the kernel. This is the kernel. It's like warping the space, going from small dimensional space to a very high dimensional space, like in here. So we went from 2D to 3D, and you can see that now we can separate, we can find a hyperplane that can separate perfectly my data points. So this is what we call the kernel. What is the kernel trick now? What is the kernel trick? Please tell me anything. What is the kernel trick? Or I will design someone. Let's see. Please, you can make a mistake. There's no problem. What is the kernel trick? This is a very important question. This is, we have how many formulation, how many construction can we have in SVM? If you remember, we had 2 formulations. Give me 1 second, guys. So in the SVM, we have 2 formulations. We talked last time about the primal problem and the dual problem. Do you confirm it? Can you confirm this?
Yeah.
Yes. Yes.
So you remember this. One is better than the other in one situation. So this one depends on the number of data points that we have, and this one depends on the number of dimensions. So if we have a low dimensional problem, this one will do better, and vice versa. But this formulation have, normally when we use a kernel, we have to compute the new x's, the new data points in the new space. Do you agree with this?
Yeah.
So,
You have to compute them.
Reza, I don't quite understand. You know, from the previous slide to here, what was the? Because we're saying, because since it's not linearly separable, we need to apply a kernel function, right, to move into another dimension. If that's the case, what is the state or the formula prior to the kernel being applied, and what's the state after the kernel being applied?
Yeah, these formulas are without any kernel yet.
Oh, is it?
Yeah, they are without any kernel. But we are saying that when we use the kernel, we have to transform our data points to go from 2D, for example, to 3D.
Yeah.
So this is what we are doing, moving from 2D dimension to 3D or 10D or whatever dimension we want to target. But we said that this process costs a lot. We have to compute from 2 dimensions, for example, 10 other values or 20 or whatever the dimension we want to target. The kernel trick avoids us this step. If you use the primal problem, we cannot avoid this step. There is no way of avoiding it if we use the primal formulation. We have to compute the new points in the higher space. But in the dual problem, we have this multiplication. We are computing the dot product between data points. So we don't need, the dot product is a sort of distance measure. We are like measuring the distance, very close to that. We are measuring the distance, something like that, not exactly like that, but just as an analogy. We are measuring the distance between xj and xk. 2 data points, we are measuring their distance. So we don't need to know exactly where they are. We can just compute some approximate distance between them, and it will do the trick. This is the kernel trick. So this is the kernel trick. Instead of computing the new points in their new space, xj and xk, what we do, we have a formula that computes their dot product directly without computing them. So, for example, we have a polynomial kernel. We can directly compute their dot product without computing the point. We skip this step. So we multiply them, the 2 points, and we just add this plus 1, put them to power d, and we have their dot product. It's very simple, as you can see. Very quick, rather than computing all of their new dimensions. It's just one single computation, and we get their dot product. Same for the Gaussian kernel. We have a polynomial, which is something like a polynomial function. And then we have the Gaussian kernel that does this formula to compute the dot product between the 2 points without moving to the higher space. We still stay in our space, in the smaller space, and we can just compute the dot product with this formula without going to that higher space. And it is infinite. It represents an infinite dimensional space. Are you happy with this?
Yeah.
It is like an infinite. If we take this, and we do the sum, like Taylor expansion, till d equals infinity, we get a formula like this. So the Gaussian kernel is like a polynomial kernel with an infinite dimension. And when we do their sum, we end up with this equation. So we go to an infinite dimensional space. And like I said last time, going to infinite is like counterintuitive. If we go to like very high dimension, our model tends to overfit because the problem becomes more complicated. We have a lot of dimensions, and we can quickly fall in overfitting. But surprisingly, the Gaussian kernel doesn't do that. It doesn't really make things overfit. to see how if your model is doing well, your Gaussian kernel, you can sometimes look at how many, like this is a good example. You remember the vector, the support vectors. What are the support vectors here? What are the support vectors? You need a coffee?
It's the two circles, no?
It's the point that are connected to the margin, which are these ones. These are called the support vectors. This. And to see if an SVM overfit, we see how many support vectors do we have. If all of my points are support vectors, I didn't say that last time, I forgot it. So if all my points become support vectors in the higher space, what does it mean?
Overfit.
We are overfitting, exactly. It means that like every point is going to some space, to its own axis. You know, when we have an infinite dimensions, each axis represent one dimension. Each axis, the x-axis, the y-axis, z, etc. So if we have one point in each axis, we might have like something like all the points become support vectors because each one is having its own corner, and we are overfitting mainly here. But here you can see in this problem with all of these data points, we are using, when we have sigma, it means an RBF kernel, that sigmoid kernel, the RBF kernel. And yet we have only 5 support vectors points in I don't know how many, in a lot of points. It means that the problem is probably not overfitting here. The number of support vectors when you go to the higher dimension can tell you if you are ever overfitting or not. Here we don't have a lot of support vectors. It means we are not overfitting. Yet we are going to an infinite dimensional space. This is really like mind-blowing, guys. And what does this sigma do, or whatever it is called? What does it do? I need some participation, guys. Why are you so tired? Why are you so tired? Guys, please, I'm begging you.
Sigma to check how much we can tolerate for the vectors.
Sorry, I didn't hear you well.
We put sigma to tolerate some vectors.
No, sigma, not C. Sigma, it's not about the vectors. Sigma tries in the new hyperspace, the infinite one, to put like some bumps around each data point. So a high sigma doesn't try to put bumps. You know, when you move from 2D to 3D, you can imagine that if we have a high sigma, take a ball, a football ball. If we have a high sigma, the ball becomes like a smooth, like in here. I have an example here, which is quite good. A high sigma means, or a low sigma, you can see the ball is not smooth. So in the higher space, each data point is creating a bump in its corner. Can you imagine it, like pushing in its corner to make a new, like something that is not flat in its space? It's like, say, a bit of a mountain in its corner, pushing things. Because we can afford a lot of dimensions, infinity dimensions. So in each like corner for each point, it's creating a bump in the like an extra dimension. It's a bit hard to imagine, I can maybe give you an example, a 2D example. So one moving from one dimension to two dimensions. Say we have these 3 points. We have 3 points, and we want to go to 2 dimensions with an analogy to this sigma. Normally, we are going to an infinite dimension, but say we are going just to 2 dimensions. If we transform things smoothly, we get something like that, maybe. So this is the first point, second point, and third point. But if we put, this is a high sigma, sigma equals 1. But if we put, for example, a sigma equals 0.1, we can get something like that. In the higher space. First point, second point, and third point.
So when you say, oh, sorry.
Yeah.
So when you say smoothness, do you mean the boundary smoothness, the hyperplane smoothness?
No, we are not seeing the boundaries yet. It's how, like, the points are going to be where they will be represented. Here instead of, yeah.
Is it the link between the points? I mean, the direction of the angle. How to, for example, from point 1 to point 2, how to link between them. So which direction I will
It's not really a
follow.
direction. It's just how it is going to be represented in a certain space. I know it's very hard to imagine because we are not dealing with the regular physics or the regular representation in space. For example, here we have these 3 points in 1 dimension. We could go into 2 dimension like that. It's smoother. But we can also go with something like that. But actually, what is happening here, it is in this 2D, it is as smooth. But if we go in 3D, we are having a bump in the next dimension in here. Same is going in here, and same is going in here. It's like creating this kind of bumps in extra dimensions. They don't exist in here, but when we move out, we can have this extra corner like. It's really very hard to explain. I will find them like a better, simpler explanation. Let's find a simpler explanation. Sometimes simplifying things is better than. So when sigma equals 1, which is considered as a high value, the support vector, the boundaries, is going to be smooth like that. You can see in here. This is an error because we allowed this. We put c equals 100, so we tolerated 1 error here. So we have like a smoother boundary. So it is capturing the shape of the whole points inside. It's capturing their whole shape, how they look like. But if sigma is small, this is the same sigma, but with a high, lower c. We are tolerating more errors here. So, but if sigma is smaller, we are not capturing the whole shape. We are capturing the shape only of the support vectors. The shape of the ball here is more like influenced by how the support vectors shape are. So here we have the shape of the support vectors in here, and this is the space. This is the margin, sorry. This is the margin. So it's like the separating margin will follow how the shape of the support vector. It's no longer something smooth. And if we make it even smaller, like this, you can see that the shape of the region is following more the support vectors, which are these points. These points. It's like it's no longer smooth. It's not taking into consideration the whole points. only the points on the outside. Same in here. Same is going in here, and we have a lot of support vectors here. So here there is a risk of not generalizing well. So we have too many support vectors here. You can see them.
So where is the hyperplane then in this image?
There is no way to put it here. We can guess where it is by doing some computation. It's probably something in here. But because everything here is support vectors, I can't even imagine how the hyperplane is here computed. It will take a lot of efforts to know where it is, because a lot of points are considered as support vectors. I can't even tell where it is. Here it is much simpler. The hyperplane, normally in the higher space, by the way, this is the hyperplane here. In the higher space, it is something very flat. In the real space, it is something like a flat, because it's a hyperplane. But when we go back here, this representation is only when we go back to the two-dimensional space. It looks like that. But in the higher space, it's something flat, but in multiple dimensions. Same in here. We could plot it. But here, I think I made a mistake. I think that even in here, no, sorry, Salsabil, I think I made a mistake. Because I don't know how this example was done. I think the hyperplane is still in here.
Yeah.
I think it's still in here. Sorry about this. I think I made a mistake, because these points outside confused me on how they were included in the support vectors. They confused me in this, that they were computed as support vectors, because in the higher dimensional space it becomes very confusing. So I think, yeah, the hyperplane is in here. Is this one?
So would you say that the boundary of the green region is called the hyperplane?
It's not called. It's because this is just a representation. Because when we move to the higher space, things doesn't look like that. Actually, do you agree with me?
Yeah.
They don't look like that. So what we did, we went to that higher space. We built that hyperplane. This is what the SVM is doing. Put that hyperplane. But when we go back here in this space, this hyperplane representation will be, it's like a projection of that hyperplane in the 2D. It will be something like that. But of course, we can't imagine how it looks like in reality, in the real one.
So it's just a representation of what it might look like, the hyperplane might look like.
It will never look like that. It's just how it is divided the space, how it is like dividing the points. Well, if we look at these spaces, this point in here, we will see that our SVM will classify it as in this region. So from this, we can infer that my hyperplane is in here. So any point in here would be classified into the yellow region. Any point in here in the green area will be classified as a point in the red, something red, in this green region. So this hyperplane is just a representation of how things are divided in the higher space. And in the higher space, things are very smooth, because the SVM is just finds hyperplanes. It doesn't find something that is like that. But because the kernel warp things, when we go back, when they are smooth in the outside the high dimension, when we go back to the small dimension, they get rewarped. So they are smooth in the higher space, but when we reverse the warping, they become like that. They are no longer smooth because of the kernel effect.
Oh, so it's just a separator, you would say then?
Sorry?
So you would just say that it's not a hyperplane, it's a separator between the blue points and the red points. In this
2D, yeah, it's not a hyperplane, of course. It's a separator reflecting the effect of the hyperplane.
Okay.
And I know it's a bit too complex when we are dealing with this, but you don't need to understand it like mathematically and like thoroughly. You only need to understand it like this sigma. When it is high, you can see that the shape is very smooth. It's taken into consideration all the points. And when sigma goes lower, you can see that the shape of the hyperplane of the warping, how we are warping things in the higher space, are like influenced more by the support vectors. So generally, a high sigma tend to generalize better. A lower sigma might overfit. So you need to test and try and see what's the best sigma in your case as well. So if we are including a kernel, especially like if it is an RBF kernel, instead of having one hyperparameter, we will have two, C and sigma. C is the regularizer of the SVM, the standard one, and sigma is when we use the RBF kernel. So we need to play, in practice, we need to play in these two values and see which one does the best job, or like which values are best in my case. Are you happy with this explanation, guys?
Yes. Okay.
Yeah.
Okay.
Yes.
More or less, you don't need to understand it like at this point, like at 100%, just to understand how, like, intuitively this sigma is affecting things. High sigma, things are smooth. Maybe we can generalize better. Low sigma, the shape becomes irregular.
Sorry, the sigma value is just for kernel presentation.
It's just for the RBF.
Okay,
RBF kernel.
RBF.
And if, for example, you use the polynomial kernel, you have a D.
We don't have. Okay.
You have a D. So in the Gaussian kernel or the RBF, sigma, and here D. And linear kernel is when we don't use anything. Yeah. Are you happy now, guys? So we said, we talked about the C, about the kernel trick, about the sigma, and about the maximum margin hyperplanes, which is what the SVM is doing. So these four elements are probably the most important concepts.
Sorry, Reda, I have one question, please. And
Sure.
in the real life, how we can decide the value of sigma? We should say the presentation, or how we can do this? That
yes,
it's a good.
There is no direct way of finding the best sigma and the best C. It's actually a try and error approach. You try and you see. And sometimes things can be not linear. For example, you put a high value of C and things improve. Then you put a high value of sigma, things are not improving. Then you put a certain value of sigma and things start improving. But at some point, you might need to decrease C and to allow sigma to move up.
Okay.
It's not convex. What I mean, sorry, it's not something convex between C and sigma. That when you improve one, you have to and then you go to sigma. For example, you improve C over C, and then you improve over sigma, and it works. It's not always like that. Sometimes you need one can influence the other, and you need to improve them both at the same time. So, and I will maybe next time I will go through this technique, how to find the best hyper. This is called the hyperparameters.
And we have to see a presentation like this image in the screen, or how we can decide it's good or no.
No, yeah, you just look at the accuracy on testing. This is a topic for today. Once we finish with this, we're going to see that, how to know if you are doing well or not.
Okay.
This is a topic for today. But there are like what we call, normally the traditional way is to do grid search. Grid search is just that you, for example, you have a grid. These are very good questions, by the way, guys. It's good that you are asking them. So you have a grid here. So here it is C, and here sigma. So you put some values in C, 0.1, 0.5, 1, 10, 120, for example, 500. And values for sigma. Actually, it should be like this. Say 0.1, 0.5, 25, 0.5, and 1. This can be typical values. There is in practice like typical values that can do more or less well. So these are my values, and you start trying. You try 0, 1, 0, 1, and you get some accuracy measure here. And you keep doing it for all the points, or every combination, and you take the best one. This is the traditional method. But as you can see, it takes a lot of time. We are going to do to compute the SVM for all of them. There is what we call the Bayesian optimization. We can have a look at it later. It takes time. This is not a very easy topic, where it can be very fast and can find the best hyperparameter, even compared to human experts. Those that are like very experienced in finding them, this method called Bayesian optimization can find the best hyperparameters in less time. It will not try everything. It has a probabilistic method of finding the best hyperparameters. We will give it some time and go through it, maybe next time or in some session. Are you happy with this, guys?
Okay. Yeah.
So just to mention again what is very important in the SVM, we talked about it is a maximum margin hyperplane. We are trying to get the maximum margin. What C represents?
Yeah. Kernel.
The kernel trick, both the kernel and the kernel trick. But we don't need in the kernel trick. We don't need to compute the new points. We just need to know how to compute their dot product. This is the kernel trick, and the Gaussian kernel is an infinite dimensional kernel. What sigma represents is how smooth things are going to be in the higher space. So a high sigma will make things very smooth. A low sigma can make the hyperplane, or the hyperplane being like not that smooth and following how the points of the support vectors are, like in here. So a low sigma might overfit. A high sigma can help to have less overfitting, but only testing can tell you what is the best sigma and the best C. So this is like what is very important to catch about the SVM, guys. So are you all happy with this?
Yes.
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 Perfect. So these are the most important concepts of the SVM. And by the way, if you like with one session and barely a half, you are able to understand it at with this with this level, I'm really happy with you guys. If you're able to understand it to this extent, it's really, really good. Okay, now let's go to today's topic. It's not as intense as last time, but it has a lot of insights. So today we are going to talk about performance measures in machine learning. How do we know that a model is doing well or not? How do we know? So far, we just used training sets to build a model. That's all what we did. We have some data points and we build a model on them. That's all what we did so far. But this is probably not enough to tell, because like we said, overfitting is a major problem in machine learning. And any algorithm can fall prey to overfitting. So the normal method to do things is that we divide our data set. When we have a data set, we divide it. We take a training set and we leave a testing set out. We build a model on the training set. We compute an accuracy on this model, and we see if the testing, when we try the testing set, we see how good it is with something that it didn't use to learn. Do you understand this?
Okay.
We use training. to a training set. But when we evaluate the model, we evaluate it into something that hasn't been used while training. This is very important. We have always to evaluate in something new that you have not used in training. This is what an exam is like. If I give you an exam exactly in what we have learned, it just means that you have just memorized everything. You memorize the book, but you can't really apply what we have learned in your real life. But if I give you an exam that has never appeared in the book, in the textbook, it means that you are able to generalize very well. So that means that you are independent. This is what we want to do. We want the model to be able to learn the hidden insights, the insights inside the training set, not memorize it. What is inside, the insight inside, and when we try them in testing, the model is able to detect what insight is inside this test, and then compute this accuracy. Generally, of course, accuracy on training is always higher, a little bit higher than accuracy in testing, which is normal. But if the difference between accuracy of training and accuracy in testing is too high, it means that my model is just overfitting, and we are not doing a good work. So, like we said, it is not enough to have just it is not enough to have a training set, but is it enough to have a test set? Is it fine? Some participation, guys. Tell me. Yusuf, can you tell me? You're not participating too much.
No, I wasn't with you, to be honest. I was with my little daughter. Reda, sorry, could you repeat the question?
The question is, well, do you understand that we are trying to measure a model? We divide it into testing and training.
Yeah.
Then when we do the training, we measure the performance on testing. Is this enough?
Yes.
I think it's enough.
It depends on what we get from testing this set.
Okay, if we get a bad value in testing, what are you going to do?
That means our algorithm didn't perform well.
So what are you going to do?
Change the model.
Model or parameter, yeah.
Adapt parameter. The model or the hyperparameters.
Yeah.
So, and say you did this 10 times and you still didn't get a good accuracy on testing. The 11th time you got a good one.
Maybe we have issue with the data set.
No, the 11th time, when you change the model and the hyperparameters again, you got a good model. So for 10 times you are trying and you got always bad accuracy. But in the 11th time, you got a good accuracy. What does it mean?
We found the good parameter.
Okay, there is another risk, guys, here. A serious one. What is it?
So this parameters is just for this data. Just a global parameter.
Your test set is influencing your decision.
Yeah.
Maybe these hyperparameters that you found are only good with your test set because your test set is guiding you. It's like influencing the model indirectly. Like a silent disease. A silent disease that is in the background. It's influencing your choices because whenever you are not making a good thing, you go here, compute some accuracy and go back. And you are changing the hyperparameters so they work well with the test set. But if the test set is like for many times saying no, and in the 11th time it says yes, there is a real risk that you're overfitting on the test set, not on the you're not learning the insight. It's like a silent control, silent like a leakage. The test set is leaking in the model without you realizing. Are you happy with this?
Yeah.
Yeah.
Okay, so this is a risk.
Sorry, Reda. So there is no way to change the test set, for example, to know if this model is performing well on this specific test set or not. It's like
There are ways, other ways, but it is not enough to use just the test set and think that it is enough.
So how if we divide this test set to many sets and testing with the same parameter?
This is a solution, yes, but sometimes the test set is taken from your training data. So yeah, the more test set you have, the less training data you have.
Okay.
So, and this can sometimes, if you don't have a lot of data, this can be a problem. So you are left with very little data if you keep dividing. But this can be a valid solution. That is what you said. It can be a valid solution.
Okay.
But you said for the test set it can be leaked into the training set, but I assume that when you're dividing the sets, so you're dividing into training set and test set, just say, I don't know, a ratio of 8:2, so 80% training set and 20% test set. What do you mean by leaking? How would it leak? Because you already divided those test sets. So how would it leak?
It leaks because of us, because of the guy who is doing the training. The method, the learning method, is not looking at this, but the hyperparameters and the choice of the algorithms are looking at this. It's us that we are making the choices when we don't have good value, good results in here. When we are doing the accuracy estimate, we are changing something in this algorithm, whether it's the hyperparameters or the algorithm or altogether. So we are keeping changing these things in here based on this. So there is a leakage, an indirect leakage in here, inside here.
Oh, okay.
And the more we change things in this box based on this result, the more leakage we are having.
Oh, okay. So the fact that we are changing the parameters in the training set, it will directly affect the test set because it's from the same set of data.
So the hyperparameters are influenced. It's not the training set doesn't have parameters. Right? It's this algorithm, the learning method, that we are changing. So the more we change this based on this accuracy estimate, this accuracy estimate is based on this, on the test set. So the more we change things in here, the more there is a leakage from here, this pipeline, into here.
Okay.
Because we are being influenced indirectly. It's like a teacher telling you, this is not right, this is not right, this is not right. And you are keeping changing your thoughts based on what is right and what is not from the teacher. And at the end of the day, you are changing your thought, but it's the teacher that is influencing you. So you are overfitting to what the teacher is saying.
Okay, I understand.
Just so I understand this, so as soon as we split the sets, so we've got training set and test set, and by going by the example of 80-20, so the training set, we apply the model to the training set, and we have have some bunch of parameters, and then we apply the model with those parameters to the test set, which we already know the outcome of, and then we see how accurate our model is in predicting the outcomes of the test set, which we all know the outcomes of anyway. And I guess we keep iterating that process until we get like a high enough accuracy estimate where our parameters are able to predict based on the test set the outcomes of the test set.
Exactly. And the more we do it, we repeat that process, the more we overfit to the test set.
So we need something like an accuracy estimate thing to check that, I guess, as in like, how would we know, is it literally just applying the model to the test set and we get an accuracy estimate? Do we need something to check the accuracy? Like, isn't there a formula where we check the accuracy estimate, or as part of the model?
There are ways that we are going to mention, of course. But what I want you to understand is that you can be influenced indirectly like that. A silent like influence. The user can maybe overlook it, and still your model is overfitting to that test set. That's all what we for this slide. That's all what we want to understand. We are going to see solutions. There are multiple solutions of doing it, but for now, this is what we need. Are you happy with the explanation?
Yeah.
Yeah.
Okay.
Yeah.
Yusuf, are you happy? He's with his daughter probably. So this is what is the explanation for this slide, and this is like a very important concept: how things can leak into the model, not into the training set, but inside the model, how things can go. So here, this is a figure about accuracy and the sample size, the training sample size. So this is for decision tree, and this is for logistic regression. You can also see that the size really matters for certain algorithms. We can't keep like dividing like multiple testing sets, etc. It can be like, it can harm certain algorithms, like the decision tree. You can see that the decision tree really likes very high samples. Logistic regression can cope with a lower sample, but the decision tree can do a very good job when you have a lot of samples. Like this is the sample size. It can do better than logistic regression when you have a very high, large sample, like in here. But logistic regression does better when we have a lower sample size. So how you divide also your test set will depend on the algorithm that you want to try. We can also, there is a solution, another solution that divide things into 3 sets. Training set, which is again divided into training set and validation set, and the test set is left out. So what we do, the learning process takes the training set, learn with it, and the validation set will be used to select the model. So the validation set is leaking inside, of course, inside the model, the algorithm, because we are using it to choose the model, so to select the model. And the test set will be checked if the accuracy is similar to the one we got in here, just to test if we like the level of leakage that we have. This is where we use the test set. If we found that there is a level of leakage inside, then there is a serious problem in my in here. The process that we did was not good. Either we repeat the process, or we collect more data, or we do something that can tackle this problem. So here, what we are doing actually is dividing things into 3 sets: training set, validation set, and test set. The validation set is used to select the model. The test set is to test the leakage. How much leakage do we have? If we do the same thing again with the test set here, we found that there is a lot of leakage, and we try to balance things with this test set. And if we use it too much, then we are going to overfit again, and we will have another leakage from the test set in the model. You can see that it is a very tricky situation. Yes, what do you want to say?
I don't quite understand the validation data set. What you said it's used to select the model.
Yes.
In what way? Can you give like an example of?
It's exactly what we were doing in here. Exactly what we were doing in here. So we have
here
a training
we have
set.
2 sets, training and test. I get that.
Yeah, this is now what we call the validation set.
Oh.
So exactly the same thing. We have the training set and the validation set. We learn the model, we test with this validation set, and we select the best one. We select the best model based on the validation set. Okay?
So what's the difference between the validation set and test set?
It's just a way of calling them. Now
So in this case, same.
Yeah, in this case, the validation set is we are allowed it to leak inside the model because we are using it to select the best model. We are not we don't use it to learn the algorithm, to learn the model, sorry, but we use it to select which model is the best. The model we train it on the training set, but the validation set is used to select the best model by measuring accuracy on this. For example, if we have 10 models, depends what algorithm are you using on hyperparameters. So we ended up with 10 models in here. So we put the validation set through them. We get the accuracies for each of the 10 models, and we select the best one. This is the process. We select the best one, but the one that did the best in terms of score, accuracy score. So we are using the validation set to select the model. Okay?
Okay.
And because of this validation set is leaking inside the model, because we might be changing different things in the models, the hyperparameters or the algorithm itself, based on this result. Same as we said the first time. So this one is just used to select. It's still leaking inside, but it is used to select. And the test set is used. Test set is not used to do anything, any operation inside. It's just used to see if the model is not overfitting to this two, to see if the accuracy is similar in the test set, just to see that.
So
okay?
is validation set essentially like another test set, but it's a subset of training set?
Yes, it's just like the test set in the first case.
In the first case, and in this case, what we're doing is, if we take the example of a very simple linear regression, we'd have betas, right? Like 1, 2, 3, or x1, x2, x3 that we want to predict. We want to train the model to get use for our estimation or something like that. Now, in that case, would the validation set, would we just keep training it such that we get good parameters?
It's up to you, but you keep training until you find out that you are getting from the validation set some good results. But after that, you need to see if you didn't overfit to the training set and the validation set. You need to see that. And because the validation set was used to do a lot of operations in here, we didn't use it to train the model, but we used it to change parameters like the C, the sigma, whether it is the decision tree or NSVM, what we are using in here. So we are making a lot of choices based on this validation set. And because of this, we should not check the accuracy only based on this validation set. It's okay to choose the model based on this and do some operations, but we have to confirm the results with the test set.
Sorry. So just to clarify, so we've got the training set, then we go to the learn models. So that's like naive Bayes forestry and SVM and stuff. And then the validation set, it's basically is used to kind of select the models amongst all the models that we've used to train the train.
Exactly.
Yeah, and then we get the model, and then we get the learn model, and that's it.
But we test it again against the testing set to see, because this validation set was used to select the model, maybe it has influenced this model, the selection, and this model will overfit. Overfit means it's going to do a good job only in this case and this case. It is a possibility because we selected it based on this validation set. We need to test it again against something completely blind, which is the test set. This test set has never met this selected model. They have never interacted with it directly or indirectly. And we want to see if the accuracy with the test set is as good as the accuracy with the validation set.
Okay, so would you say a validation set is like a filter of learning models? So you kind of filter through which model is the best. for
yes,
our
exactly.
training.
Now you can call it that way. You can call it that way. But that filter can overfit. It can do a good job, but it can overfit at the same time.
Okay, makes
And
sense.
we want the test set to see if that filter did overfit or did the right decisions, made the right decision. Are you happy with this explanation, guys?
Yep.
It's really like a silent effect. This validation set can really silently affect the model without you realize it. Because if you never got some good results in here, you keep adding models. You keep adding models in here. Learn new models. For example, if you have an SVM, you change its hyperparameters, which makes a new model again. And you keep doing it until you find good results, some good model. But this model, we have no guarantee that it is a good one or just a one overfitting the validation set. Are you happy? This is the most important concept that we need to understand here now, today. But things can indirectly leak inside your models. Knowledge can leak inside, and this can lead to overfitting. Give me some body language, any sign, guys, because I can't see your faces.
In the test set. So we test like new cases or new.
It's some new cases that were not observed in here and in here.
Yes. Real.
Yeah.
Okay.
Exactly.
And can't be like difficult and like maybe like put like the model not accurate.
Sorry, I couldn't hear what you said.
So maybe the model at the end failed at the end.
Yeah. If we find that the test set is giving bad results, it means that we had just some overfitting on the validation set.
Okay.
And this process can be repeated, by the way. If you keep doing the same thing with the test set as we did with the validation set, then this can also leak inside. But the more you repeat it, the better the model becomes. But it can be really a tricky situation. But it doesn't happen a lot in practice.
What's the split from the training set to the validation set? Is it like another 80-20 again, or
something? Generally, it's something like that, but it depends. Yeah, 80-20 is a common value. Yeah.
Okay.
It's like when you have an exam, you are like revising. In the beginning, you're revising your course, and your validation set is you try some exercises because these exercises didn't appear in the course. So if you are able to solve all of these exercises, but you did bad in the exam, it means that you didn't. Your exercises were not that good. They did not generalize very well, or you just learned how to solve these exercises, which is the validation set. But if you did well in the exam, it means that your exercises didn't leak much inside what you learned. It means that your exercises are representative of the world, of what is happening in the exam, etc. So it's like if you look at something, it's going to influence you.
At which point do you? So once we've done this and we've tested against the test set, I guess we'll get an accuracy estimate, and would that be the final kind of result? The example.
Yeah. If it is a good estimate, if it is a good accuracy comparable to the validation set accuracy, it means the model is doing well. If it is not, then you are going to repeat the process.
Start all over again.
And probably, sorry, yeah.
Start all over again.
Start all over again, and if you do it a lot of time, this test set might start leaking in the model.
I see.
So maybe you have to collect more data in that case to do a better training, a better validation, and a better testing. So maybe your data is not really good to train your model. You need to do more sampling or any method that you are using to collecting your data. Okay, but this is like an extremely important concept in machine learning. Very, very important. Now we are going to see another technique that can, for some of the problems of this division is that maybe you don't have a lot of data to divide your training set and your validation set and your testing set. So there is what we call, and also one testing process might not reflect the behavior of the model for a particular instance, because this instance occurs rarely inside your testing set, but it might occur multiple times in your real life. So what we have here, we can do what we call random sampling. We repeatedly randomly sample testing and training. So we just repeatedly take some training and testing, and keep doing this again. This is just to see that our tests are like they don't change a lot. The accuracy measures, for example, you take an algorithm, you apply it, you don't change it. Let's say an SVM with C equal 1, sigma equals 0.1 or whatever, and we use it for training and for testing. We do it again with the same hyperparameters, but with a different portion of testing, of training and testing. These are like selected randomly, random partitions. And we see if testing is similar across all the different partitions. This is just to make sure that the hyperparameter that we are choosing are consistent over different portions of the data set. Did you get it? Did you get this one?
Yeah.
So this is just a randomly sampling. That's why I said that this is like not a very complicated topic, but it has a lot of insights on how data behaves, models and data, how they behave, sorry. So here what we want to know is if my model, maybe we got like a good accuracy on training and testing by chance. This is a possibility. So what we want to do different divisions of training and testing, not just one division, randomly. For example, in the beginning, in the first one, we select the first 100, the first, say, 80%, and the last 20%. In the second one, we select the training in the middle. The third one, we select the training at the end. So we end up with different training and testing. And we see if the accuracy doesn't change when we train different models, in here and here and here, if the accuracy doesn't change when we do this process multiple times. It just tells me that my model or my hyperparameters are like good, or at least they generalize well with my training set. But by the way, when I do that, when I train in here I train a single model. When I train, this model in here and this model in here will be different, even if they have the same hyperparameter. Say, for example, if I use here an SVM with C equal 0.1 and sigma equal 1. If I use this in all the models, but with different training sets, the hyperplane that I'm computing will be different. Yes or no?
Yes.
Yes, because
Yes.
the data set is different. The data set is different. But I want to see if this difference doesn't affect testing too much, the accuracy in testing. If the accuracy in testing is fine, it doesn't change too much, it means that these hyperparameters are doing a good generalization in my data set. Okay? We can also do what we call the stratified sampling. So here we try to keep the classes proportion when randomly sampling. We don't want like one sample, say a training set. We have a training set like that. This is a training set. And if it ends up randomly to become like that, plus, 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 and only one single minus, It's not really good. The data became unbalanced. Just one single minus class, one negative class, which means second class, and all plus classes, positive class. It means the model is not going to do very well. It's just learning the positive side, but it does not learning the negative class. So for the stratified testing as a sampling, we keep the proportion. So if we have, like, say 40% negative, so and 60% positive, we keep the same proportion when we divide. 40%, so sorry, 60%, 40%. Same in here. 60%, 40%. So we want to keep the same amount of instance per class. So what we call this stratified sampling. So just to have the same proportion. Otherwise, if we don't have the same proportion, like the model will just focus in one class, and the other model can focus in a different class. Are you happy with this explanation, guys?
Yeah.
Yes.
Okay. Now the famous cross-validation. This can help a lot when we don't have a lot of data. So what we do in cross-validation, we partition data in n subsamples. For example, this is all of my data. Say we divide it into 5 subsamples. 1, 2, 3, 4, 5. 20% each. And so here n equals 5. And then we train the models. We train n times on n minus 1 partitions and test on the remaining one, which means that we take one of them out in each step. In the beginning, we take S1 out. We train on this, and we test on this. Again, we do the same thing. S2 will be testing, and the others will be training. Same for S3, S4, S5. So we end up with 5 iterations, and each one of them will test in a different subset that was not used in training. What is good here is that when we are testing in all my data sets. We are testing in all of them, all of the data of my samples, all of the data points. Here we are testing in here we are testing in S1. Here we are testing in S2, S3, S4, S5, but with different models. They have the same hyperparameters, but the computed model is different. So we are testing in all of them. If we have 100 samples, we are testing in 100 samples. Instead, like in the previous case, we were testing only on 20%. Do you see the advantage here that we have? Can you see the advantage?
Yeah, we have a valid, like a valid test and real test. So we can select a good model.
Yes, but what we are doing is that in the beginning, we were testing only on a subset. Like in here, in the validation set, in here, we were testing only or validating only on, let's say, 20%. But in here, no, we are doing this testing in all of them. All of them. Of course, we are doing things 5 times, but we are testing in all of them. Are you happy, guys?
Yeah.
What are the S's?
The S's are the divisions, the different subsamples.
So in this case, are they all equally split?
Equally split, yeah. N subsamples equally split, S1, S2, 20% each.
Okay.
So we have this split, and we leave one out. We train on 4, and we test on the 5th one. Same thing. And the 5th one was not used, of course, in training. And we end up testing in the whole dataset. So we can have a bigger overview. However, in this case, are the models that, say, for example, we are using an SVM, a linear SVM, simple one with C equals 1. We are using it in here, in here, in here, and all of them. Is the model, the SVM with C equal 1 trained in all of them, the same or not? Is the hyperplane computed in here, here? Are they the same or not?
It's the same model.
Yeah, it's the same.
No, why would it be the same? It's trained on different data.
But we are talking about the algorithm and parameters. This is what we understood. It's like the same.
The SVM we see, the algorithm is the same, but the
It's
hyperplane,
the same, yeah. Okay.
The hyperplane that is computed in here to separate my data is not the same in here,
Yes.
in here, because it's logical. The data set is different. As long as the data set is different, the hyperplane will probably not be the same. It could be the same, but it's very rare. But it should be, if we are doing a good job, it should be like very close. This hyperplane should be close to each other, very close ones to each other. So what we are evaluating here, are we evaluating a model? Like we said that the models are different. A model is what is basically the hyperplane here. They are different. The model here and here and here are all different. Do you agree with me?
Yeah.
But excuse me, but why
Yes.
why we have a different hyperplane? When the data follow the same model or the same feature, we should have the same hyperplane.
Yes, this is when you have the data exactly very close to each other. But chances are that these data are different. These data are different. This one, they are not the same. Here we don't have S1. Here we don't have S2. Here we don't have S3. So the portion that is missing will influence what hyperplane we are computing. If the SVM is a good choice, SVM with C equal 1, we will end up with different hyperplanes, but not too different, close to each other. If the SVM is a good choice.
Okay.
But still, because the data is by definition, if the data is different, the SVM will probably be different. The hyperplane model will be different. Here I said we are still using SVM with C equal 1, equals 1. So what are we evaluating? We have 5 different models. We have computed 5 different models. Do you agree?
Yes.
So we have 5 different ones because we are using different data sets for them. Even if they can be very close to each other. One can be like that. The other one can be like that. Other one can be like that. Slightly different, like small differences, but they are still different. There is a chance that they can be identical, but a very low one. So what are we measuring? What accuracy is this? These accuracies are of this model. This one is for this model.
Yeah.
Yeah. So these are the accuracies for each model, because we have 5 different models. But this accuracy is not for one particular model. It is an accuracy for what?
For the
For the
5.
algorithm?
For what?
Maybe for the algorithm?
It is an accuracy for that C, for that SVM plus what we did to build my model. It's the hyperparameters, actually. It could be other things, like if we are using some pre-processing, like scaling the data, like it is the process. We are evaluating the process that we have done to reach these 5 models. Here, in this case, it's SVM C equal 1. SVM with C equal 1, we are evaluating this, how this is performing in here. And this is its accuracy when we use cross-validation. We were able to validate it in the whole data set, because we are evaluating in all of them, but with the cross-validation trick, we could do it without leaving anything out, or everything is used in testing. So, but we are, like I said, we are not measuring the accuracy of a model. We are measuring the accuracy of a particular technique, of a method altogether, which is this. Okay, guys?
Yeah.
Reda, how would you differentiate between a method and a model? What's the difference?
A method is what choices are made before starting to build the model. These choices are, we said it's the SVM. We want to do this. We fixed C equal 1. If we had a sigma, we add sigma equals something. So this is the method. It's like what we call the hyperparameters. And the model are the parameters inside the model. So we have two things. We have the model's parameters, and we have methods parameters, which is the algorithm, the choice of the algorithm, the hyperparameters, which is here C, sigma. If it is a decision tree, it could be the length of the tree equal 3 or whatever. If it was the KNN, what would be the hyperparameter?
Okay.
K, yeah. So this is the method, and the model is like trained after fixing these things. When we fix the algorithm, the hyperparameters, sometimes pre-processing, like scaling. If you remember feature normalization, we talked about it in making features having the same scales. Like if one is like, one feature is its maximum value is 1, and the other feature its maximum value is 1 million. We try to divide that feature by 1 million to make them having the same scale, to be comparable in terms of value. This can be also included into here, into this zone. Feature normalization. Sorry, I can't even write properly. Features normalization here. So this is the space of the method, what we are using. And the model is when we compute the parameters of the model. Is what we optimize. This, to make this clear, these are chosen by yourself. Yes or no? These are chosen by yourself. But these parameters inside are chosen by what? Who chooses these parameters of the model? By what? They are chosen by the algorithm itself, the optimization. Like the hyperplane, the W's of the hyperplane. But these are chosen by the algorithm that is trying to optimize the model. And these are chosen by yourself. I really want to look at your faces, guys. You are not giving me anything.
Sorry, Reda, this point I didn't understand it well. The difference I know is like the method is the parameter that we set, but I don't understand what is model. What do you mean by model exactly?
The model, for example, if we are dealing with the SVM, the model is the hyperplane. And the hyperplane is found by whom? Did you choose it yourself? No.
No, by algorithm.
By the algorithm.
By algorithm.
The model, exactly.
But C value it's fixed by the who fixed the C? It's us who should fix the C value and the theta.
Generally, it's you. It's considered as you who fixed the C value.
Okay.
The C, the algorithm, the scaling, the L in the decision trees, the K in KNN, they are fixed by yourself. But the model's values are chosen by the algorithm. For example, in the SVM, the gradient descent, or whatever method, optimization method we are using, we choose the best W's that satisfy my cost function. So these are called the values of the method. And this is called the model itself. So here, when we do that, because we are dealing with different models, we are evaluating this zone. We are evaluating what we have here. Your choices. In other words, you're evaluating your choices. The choice that you used to build this model. And this is a way to evaluate what you are doing. If your choices are good or bad. It is called evaluating the structure of the model. We are evaluating the structure of the model, not the model itself, but like its skeleton, like its how do you say that? We are evaluating like its body instead of the mind yet. We are evaluating the body of the model, but the mind is computed later. Or if you prefer, we are evaluating the DNA of the model, not yet the real person. We are evaluating its DNA. So this information can be called the DNA. And once we start building the model, the hyperplane, like in SVM, we create the real model. It's like more the abstract form of the model. These values are the abstract form of the models in here. And when we use them and we optimize, we start the optimization process, we build the model based on these values. Are you happy with this explanation, guys?
Would you say, Reza, that the accuracy is dependent on the method then? Because the method is what we are choosing. Like we're changing the C and everything. So the accuracy is basically blatantly dependent on the methods and not the model itself.
Exactly. And because the model, the algorithm that you are choosing is inside the method as well. And we are evaluating multiple models. So each of these methods values will produce different models. And of course, we can, this will never evaluate on a single model. The single model has this evaluation for it. But this will evaluate the whole method. The whole method that we followed in here. So we are evaluating your choices of the hyperparameters. Are you happy with this, guys? This is a very important concept, and it can really help in interviews. They will ask you this kind of questions.
So, for example, Rida, for example, just to understand, to change from the SVM, let's say that we have decision tree, like a model. So now the model will be the trees and the depth of this algorithm.
Yeah, the hyperparameter of the decision tree will be its depth. Yeah.
Okay. So and we have to set. So the depth of the either it will be, for example, 4 or 5, the depth of the trees.
So, yeah. So your choice is just that you choose the decision tree, and you choose the depth.
Yes.
So you are evaluating these two values, if you did a good choice or not.
Okay.
And if you, for example, did feature scaling or whatever pre-processing you've done, we are going to look at this later in the next chapter. Not when we start with, especially with unsupervised learning, we have some very important concepts there. We can see that you can do some pre-processing. We can even do something that we call feature selection. We haven't seen that yet. We are going to look at it before unsupervised learning. So we are evaluating all of your choices with this method, with this cross-validation. Because it can't evaluate a single model. It doesn't have a single model anyway. It's not using a single model. Are you happy, guys, with my explanation?
Sorry, just one more thing. I mean, I understood now with accuracy. So where does the model come now? Accuracy is based on the method.
We are not evaluating the model here. We can't.
So there's no model here then. We're just based on everything is based on method.
Yeah, we have 5 models. In practice, what we do, I will explain it on one of the slides. There is something about it. A slide can help me better to explain it. How we do things in practice. So here we are just measuring our choices, measuring how good are our choices with cross-validation. Just to complete with cross-validation, we return back to this aspects. So generally, 10-fold is very common when you use 10, which means 90% are used for training, 10% for the validation, and we repeat it 10 times. But also small values are used, especially if the learning is very slow. In some classifiers, learning can be very slow, and 10 models can make cost a lot of computational power. So we can revise it to a smaller number. What is good also about cross-validation is that it uses the available data efficiently for testing. It uses the data very efficiently for testing. So we use all the data for testing instead of just a small portion. So it tells us how our choices are affecting across the whole thing, other than a small thing. If n equal the number of instances, for example, if you have 1,000 data points and n equals 1,000, which means n 1,000 folds, then we correctly leave one out cross-validation. But this costs a lot. You train a model, says, on 99,999 samples, and you test only in one. But this will cost a lot of time. In practice, we never use it. So with cross-validation, we are evaluating the performance of a method, like I said. Example, algorithm and set of hyperparameters instead of a particular model. That's what I was explaining. We are evaluating the performance of a whole method rather than a particular model.
What's the difference between the method and the model? You mean like what we just discussed? That being the method.
Yeah, the method is the selection, your selection of the algorithm and the hyperparameters. The model is a single model in here. So the model is a single one. I will tell you more about it. I think I should give you a pause, no, guys?
Yeah.
What do you think?
How long are we going up to?
Yeah.
Just let me see how many slides I still have. This one are rather simple. Yeah, we don't have probably half an hour more. Probably half an hour. So let's take a 10-minute pause.
Yep.
And we come back. Okay, guys. See you in 10 minutes.
Okay.
Thank you.
Thank you.
This conference will now be recorded.
So we were in here. So here is the method. Yeah. Here is the method of how we select like the best model, the best structure of the model. So when we use cross-validation, so what we do, we use cross-validation, we learn a model, pick the best, and see how it is performing in testing. This is this algorithm, how it works in terms of steps. So for example, finding the best K in KNN. So we use this method like to find the best structure or the best method. So we do the partition training into the folds if n equal 10. Then we divide things into 10 partitions. And we have, say, some values of K. We take K equals 3, 5, 7, 9, and 11. So we took 5 possible values. So for each K, here what we are doing, we want to select the best K using cross-validation, just to make sure that our K is the best using cross-validation, not in just one simple division, by looking at different testing and training partitions. So for each K, we select the first K equals 3. And we start for I equals 1 to n. N are the divisions. So for each portion that, of the data set, we learn a KNN model using all the faults exactly. So we use that K equals 3, and we do the cross validation. K equals, say, N equals 10, for example, and we do that cross validation. So we end up with a accuracy measure. So if we have, for example, we had 100 samples, the number of samples equals 100, we end up with an accuracy measure, let's say 80% for the first K. This is what this means. Learn K model using all cross validation, all false path S1. Evaluate accuracy on Si. So it's exactly the cross validation technique. So we end up with measuring all the accuracy across the 10 tests, and we sum them up to see what is my accuracy. And we select the K that resulted in the best accuracy for all of them. So this way we know what is the best K. And then what we do after that, learn the model using entire training set and selected K. Do you understand this bit? So what is this going to? Guys, anyone? Do you understand what we did in number 4? From 1 to 3, the regular stuff. So we picked a structure of the model, a K equals 3. We did the cross validation for it, dividing by 10 or K n folds, evaluating across all of them. Let's do 10 training, evaluating 10 times, doing the sum, seeing the accuracy score for K equals 3. And we do it for all the Ks. So for each value, okay, we do it for this, for this, for this, and for this. And we end up with with some accuracy for all of them. And what we do, we select the best K. Say we found out that K equals 7 gives the best accuracy. So what we do after that, because we don't have a single model, do you agree with me? When we use cross-validation, we have, how many models do we have per K?
Depends how
many?
10 here.
Yeah, if n equals 10, select
yeah.
is 10. So we end up with 10 models.
Yes.
Each model is slightly different than the other. Each model is slightly different because they don't use the same data set. So we ended up with 10 models. What we do, once we select the best K, this is the process. Once we found out that, for example, 7 is the best, what we do, we combine the data, again, all together. All the 10 faults, we combine them again. And we train a whole new model, one single model containing all the data, the 10 faults, with the best. So here we train one single model, K equals 7, with everything. Because we saw that the best K in here is K equals 7, the best structure that works when combining different faults. We found out that K equals 7. And after that, normally we have number 5. What do we do? What do you think we do with number 5?
The accuracy, we need to check the accuracy.
For what?
For the different model.
We have one single model now. We have the bigger model. Once we selected the best K, we trained one model. So where are we going to evaluate it? This model is using everything we have. All of the training that was in here. Sorry, in here. We are going to in the set. And we have a testing set as well. Testing set. So we do all of this on the training set. We get this model in here and we evaluate it into the training set, the testing set, sorry, that was not used to do this part. This is how we use cross-validation to pick the best hyperparameters and the best model at the same time.
Okay.
It's not guaranteed, by the way, but it tends, in practice, it tends to do a good job. This process, in practice, tends to do a good job. It will never be, never guarantee that it's going to, we have here the best model. But in practice, it tends to be good. So what we do, we take the training set. We have the values of our choices, which is the method. This is the method. KNN plus Ks. And we try cross-validation for all of them. K equal 3, 5, 7, 9, 11. And after this, we select the best K based on the validation, because we have the 10% the validation set, and we see the accuracy. The best one will be picked, and the best K, of course, will be picked. Because we have 10 different models, there is no reason to pick one instead of the other. We don't know. We combine again the n faults, the 10 faults here, in one single data set, and we train the KNN with K equals 7. And we test on the testing set that was left in the beginning. It was left out in the beginning. This is how to pick the best hyperparameters and training a model with cross-validation. And this method tends to do a good job in practice. Did you understand it?
Yes, it's.
Excuse me,
Are you happy
Reda.
with it? How? Yes?
Yes. This process of validation, it's applied just for KNN, or we can apply it with SVM?
You can apply it anywhere. You can apply it for every model. If you want to apply it to use it for different models, you just have to add a step here in selecting from SVM, KNN, decision trees, and you do it for all of them.
Okay.
But the drawback here for this method is how many SVM, sorry, for KNN, how many KNN do we are going to end up in here trying? How many?
5.
It's number
Why
of K.
No, the number of K.
Yes, 1, 2, 3, 4, 5.
It's 50.
50?
We are going to train 10 models here.
10 multiplied by 5.
Exactly, and 10 for each K.
Yes.
So
yes.
it's 10
yes,
multiplied by 5. So it's 50 KNNs.
Yeah,
which can
right.
cost some time. It can
Yes.
cost some time to use it for 50. It's 50 KNNs. And if, yes?
Yeah.
So here where S1 to Sn is essentially the partitions like you mentioned last time when we had 5.
This is the these are the partitions. So 50 KNNs we are, and if we have more hyperparameters, say in SVM, if it is an SVM with a sigma and a C, and we have, say, 5 values of sigma, 5 values of C. So how many SVM are we going to train? Sigma equals 5, C equals 5, and N equals 10. False. How many are we going to train?
Multiplied by 5, it's
25 multiplied by 10. No?
250.
250.
250.
Exactly. 250 SVMs, just to pick the best ones, because we are trying all the combination possible.
But the number of occurrency, it's depend of the number of K.
I can't hear you.
But the number of occurrency.
I can't hear you.
I don't know. But the number of occurrency value is depend of
the number of what?
The number of K, or no?
No. Here in the SVM we don't have a K.
I think I have problem in my.
I can
No,
hear
Mohammed, we
Yeah,
hear you.
in the SVM,
clearly.
Yeah.
Clearly.
Yeah, in the
I
SVM we don't have K.
Yes, I know, but in this case of KNN, the number of currency that we should have in the end, it's the depend on the K number. No.
Yeah, it depends on the K and N, of course, the division.
Okay.
How many divisions are we going to divide? Because this always also determines how many training are we going to do.
Yeah. Okay.
So in this case, it's N multiplied by 5, 50. In this case, it's 250. Because we are trying all the combinations possible between sigma and C, which are 25 combinations. This, if you remember that matrix I drew. Plus, we do it for multiply. So for each one of them, we do it 10 times. And after that, if we are doing it for the SVM, after that, once we pick the best sigma and the best C, we train a new SVM here, a whole new SVM that is using the best sigma and the best C, but with combining all of the portions. So we have one single data set, the bigger one. And we still do the validation here. Sorry, the testing. Validation is in here. Testing now. We test on something that was not used in here. So this is how in practice we do things. So this cross validation is really a good way in finding the best method, or not really the best, but something close to the best. The best method here, for example, SVM plus sigma plus C. And you can try multiple methods, not just the SVM. You can try the SVM, you can try KNN, you can try. So you do it for all of them, and you pick the best one, the best accuracy. Okay.
Okay.
Are you happy with the cross validation? Picking parameters with cross validation, hyperparameters. Sorry.
Yes, Rida, sorry, I was like arrived late, but here I think you explained what you explained before for the post.
Yeah, but here it's to find the exact. I explained this before, but we added this by a bit.
Yes.
We combine all the data once we find the best K or whatever hyperparameters you're using. We combine them and we build a new model altogether using all of the data set. This is we use this just to make to have like little influence from the testing or from the validation. We try to like minimize the influence. Okay, now the confusion matrix. So just to highlight the important aspects of today's session. The first important aspect is
just one question. So Rida, the cross validation, it's combine all the first method that you explained in the beginning.
You mean from the beginning that we started learning machine learning?
No, this method and the other of subdivide the set. It's combined the two methods. This is the thing.
Yeah, well, yeah, you can say that it combines the subdivision plus training a new model.
Okay.
If that's what you mean.
Yes, this.
So we add the extra step.
Okay.
So what I want to highlight is the important aspects of today's session. For today, one of the most important is the cherry testing set leakage, that it can leak into your model. This is a very important concept that we might like lose when we start reading about these aspects. So testing can leak into your model. Are you happy with this concept?
Yeah.
Okay.
All of you?
Yeah, this is the problematic.
Testing can leak. Yeah, can leak. When you are training and you see that according to your testing, you're not doing a good job, you are modifying your learning method. your hyperparameters or whatever according to the test, and you are doing that repeatedly. And because of this, some information in here are leaking indirectly through yourself. They are not leaking inside through data. They are leaking inside because of you, of your process. You know, I wanted to mention, this aspect of physics. When you have, say, a photon going inside, like you are releasing a photon going into a particular direction. And here you have a hole, and you see where the photon is landing. It is going into direction in here. But if you try to measure where this photon is going, if you measure its direction, it can go to a different trajectory. It's because your measurement, when you are looking at the trajectory of the photon, trying to read its trajectory, you are influencing the photon. This is like a very famous concept in physics. You try to measure the state of an electron into these small elements, small particles. You try to measure its state, you influence it. It's not like so your measurements is false. It's not a real measurement, because your tool that you are trying to do to measure that thing, that state of or the trajectory of the photon, is going to affect it. It's so sensitive that it is affected by the measurement tools. Something comparable is happening in here. When you try to measure a model and change it according to this, this is influencing it indirectly through yourself. It's like so some irony here. It's like the testing set is making fun of us. It's playing with us. The testing set is playing with the data scientist. This is what is happening in here. That testing set is like manipulating you to get some good values, but what you are really doing is that you are just following what like the mood of this testing set, and nothing is really, no data is 100% trusted in real life. So this is the first concept I want to highlight for today's session. And the second one is for cross-validation. That cross-validation can measure the structure, how good the structure is, or the method, not just the model. The model is learned after fixing the method. So it gives you like some estimation of your method that you are using. KNN with a particular K, SVM with a sigma and the C. This it measures this. But after this, when you use cross-validation, we pick the best values, the best method, and then we train a whole new model on it, on the whole data set. We still need to evaluate it on the testing set, guys. So these are the two most important concepts that we did for now. We're going to add the third one. Are you happy, guys?
Yeah.
Reda, if you go one slide back, please.
Mm-hmm.
You know the table one for the accuracy?
Can you hear me?
Yeah, I can hear you now. Yeah.
Sorry, I had a problem with my audio.
No problem. No, it's you know the table for the accuracy.
This one.
Yeah, this one. Yeah. Just a quick question. You know the correct values you've obtained. Is that computed, or how did you obtain that?
It's on the computed on the S1 here, S2 on here, on the testing. It's computed on testing.
Okay. Okay.
So for this model, it's computed on this. For this model, it's computed on this. And then this is the sum in here. And this is the total accuracy of the method. Okay,
Okay, so 11, it's come out of the fact there's like 5 data set. How did they get 11?
So we have 100 samples. So 20 sample per test set. Here we had 11 correct and 9 incorrect.
Okay. Okay.
Same for all of this. So 11 correct, 9 not correct, 17 3, etc. So that's the results of each model, the 5 models. Are you happy, guys, with these 2 concepts that are very important for today's session? Data, like this leakage, models leakage, data leakage indirectly through your process, and how cross-validation is used to pick the best structure of the model or the method if you prefer.
So far, so good.
Okay, Yusuf, are you happy? I'm not hearing your sound, your voice too much. It seems he's not with us. Najwa, are you happy? You're too silent. Sorry?
My cafe is off. Yes, I'm happy.
I couldn't hear you. You're happy. Miriam, are you happy? You are always very dynamic with our sessions.
Yeah, that's okay. I think I need to with fresh mind to read it again tomorrow and to get across it.
Okay. Okay, we can do a revision next time again.
Yes.
Yeah,
so
that'd
let's
be good.
go to the last aspect. Yeah, I'm happy to revise them again. The more you do them, the more you absorb them, these concepts. But I for today, at least I want you to understand that how leakage happens through our process, through what we do. If you are happy with leakage, how it happens, that's already good. So the confusion matrix is something that tells us these are our classes, and this is what the model recognized. So what we want is that the diagonal will be 100%, the maximum. So if this is what the actual class, and we recognize it as this class, this will happen. We will have a number here. Let's go to this. This is more simpler. So this is the predicted class, and this is the actual class. We can reverse them if you want. So the confusion matrix tells us what did we predict and what is the real class. So if the real class is positive, and we predict something that is positive, we get a value here. So say we have three in my data set. So this is the label. So we have class 0, 0, 0, 1, 1, 1. If we predict this is the correct class for my data set, this is class 0, which is positive, let's say. So if we have here 3, and in my model we got something like that, 0, 0, 1, 1, 0. So we did 2 mistakes in the model. The model did 2 mistakes here and here. So my confusion matrix will look like something. Say this is actually the real class, and this is the class. So this is class 0, 1, 0, 1. So how many predicted class did we predict accurately when it comes to class 0? How many? How many were class 0 were correct?
2.
So we put here 2. Yeah. How many class 1 were correct?
2
1.
as well.
Also.
Yeah, 2.
Mm.
Here I want to 0, 0, 1. Here another one, sorry. Here we have another one. So 2. How many class 1 were mispredicted? Class 1 were not correctly predicted.
1.
1.
That's 1. And how many class 0 were mispredicted?
1 as well.
1. So this is how we plot confusion matrix, just for two things, for two classes. For multiple classes, it's slightly more complex, just slightly. So this is the confusion matrix. It gives us a bigger overview of how my model is performing for each class, not in general, but for each class. Accuracy is very simple. When we want to compute it in the confusion matrix, these are what is correct, and this is the total number of cases. So the accuracy is this and this, true positives and true negatives, what is true, divided by the sum of everything. This is the accuracy. We divide what is correct by everything else.
Right.
Yes.
Yeah.
Rida? Excuse
Okay.
me.
Not hear me.
Rida, hello?
So because accuracy may not be a good measure,
Rida, we are getting you. Not
Rita,
well.
we cannot hear you.
We don't.
Hello.
for example, we have an accuracy of 90.
Sorry, Rida, we are not getting you well.
Can you hear me now, guys?
Yes.
Yes.
Yes, perfect.
Clearly?
Yeah. Welcome back.
Can you hear me clearly?
Clearly, yeah.
Yes.
Yes, yeah.
Yeah.
Yes.
I can't hear you well. Say when you have
Oh.
95% accuracy. Generally, is it good or bad?
Sorry?
You were cut off. We couldn't hear all the sentence.
I can't hear you. I think I have a connection problem. I think I'm going to turn off the camera and see. Can you hear me?
Yes.
Yes, sir.
Yes.
Yeah.
This is
No, I
good
can't
now.
hear any of you.
But we can hear you.
Can you just write it down? I can't really hear you. Now I can hear you. Can you write down on the chat if you can hear me? Or
Okay.
if
Yes,
anyone
yes.
can't,
We can hear you. We
write
can hear
something.
you. We can hear you.
Because I can't hear you clearly. There is some problem. Perfect. So guys, when we have a 95% accuracy. Is it generally good or bad?
It is good.
Yeah, it's good.
Generally, yeah, generally it is good. But imagine that 94% of the instances belong to class A. So the model that classifies every instance into class A will achieve 94% accuracy. Yes or no? So just a model, very naive one, that puts everything to class A, it doesn't care, will achieve a 94% accuracy. Do you agree with this?
Can you say it again, please?
Can you still hear me?
Yes.
Oh, no. I can't hear you at all. I think I have a connection problem. So we will revise. I will continue talking Allah, but we will repeat it next time because I can't hear anyone. If you have any question, please write it down in the chat.
Okay.
So this is really bad in machine learning. When you have this class imbalance problem, a 94% accuracy, a data set consisting of 94% in a particular class will be like class. Accuracy alone is not value of classes. Sometimes depends is more important than the other. For example, if detecting a cancer in a patient, detecting or not detecting, or say or not,
Can't hear you.
the two classes are.
Hello, Reda. I can't hear you.
He has problem, I think, with them. Yeah.
Yeah, problem here is writing. Oh,
He say, let's stop here, I guess.
yes.
He said, let's stop here.
Yeah.
Yeah, this is
I
what
think,
he said.
yeah.
Yeah,
Oh,
he said.
yeah. Was he saying let's stop here? Yeah. Okay. Text him separately, and we just carry on next time.